Welcome back. So this is the first actual proper content video in this series, and we're going to start by looking at Unit 1 information representation. And as always, if the video is too slow, then I recommend watching at 1.25 or 1.5 times the speed. Right, so let's quickly have a quick overview of the entire chapter. I guess I would suggest doing this as well, when it comes to revision. Read over these, chapter, learning objectives, make sure you understand all of this. Just as a kind of, sort of self-check mark or, self-analysis, for, what you know and what you don't know for the exam. But anyway, so what we need to do then, we need to understand what binary is, We also need to understand what denary is, or, denary decimal. We need to understand different number systems, and, the three we're going to look at is going to be, binary, denary, and hexadecimal. So binary being base 2, denary being base 10, then hexadecimal being base 16. Of course, there are also more. There's actually like an infinite number of number systems. These are the three that are sort of commonly used, in computing. Then we want to perform binary addition and subtraction. Now, technically, subtraction you can do just by using addition. Let's say just by adding a negative number. Because if we think, let's say 5 plus negative 2, that's just equivalent as doing 5 minus 2. So we can see here, that kind of doing addition of a negative number, can be used to simulate subtraction. I guess of course it is good to actually know the, sort of the real method of doing subtraction, rather than just kind of simulating it, by plussing a negative number. Then we also, we want to understand BCD, binary coded decimal, hexadecimal, and also where they're both used, for practical applications. We want to understand, different character sets. So the two character sets, and where's the pen? Okay, there it is. It's really difficult to see this marker here. So the two character sets, one is going to be ASCII. And ASCII, this can use either 7 bits, 7 bits in standard ASCII, what's going to be 8 bits in extended ASCII. Therefore, with 7-bit or standard ASCII, we can represent 128 different characters. Which honestly, that's not very much. That's basically the number of keys on your keyboard. When you also consider the enter key, the various punctuation. Then extended ASCII, that's going to be 256. And again, here it is. 256. Then of course, as you can imagine, this is obviously not enough. So then we're going to have Unicode. Now, Unicode, this is going to be a variable length encoding. If we're talking about, let's say, not Unicode 8, but something called UTF-8. Now, UTF-8, that's going to use between 8 and 32 bits. And basically, this is going to give us millions of different characters. So all of the languages, all of the emojis, all of the mathematical symbols. Then we want to understand what a bitmapped image is. So bitmap, JPEG, PNG, GIF, sort of WebP, etc. We want to be able to calculate the file size for a bitmap image. We also want to understand the effects of changing elements of a bitmap image on the image quality and file size. So, for example, if we change the resolution, if we change the bit depth, the color depth, and actually, those two terms are equivalent, Bit depth, color depth, it means the same thing. Then we want to understand what a vector graphic is, and also how data for a vector graphic is represented, or encoded. Then we want to say, what's the advantage of a bitmap? What's the advantage of a vector? And when would they be used? Then similar for sound. How is sound represented? How is sound encoded? What's the sampling rate? So the sampling rate is basically how many samples or how many measurements of the sound that we take per second. Then the sampling resolution, this is what the number of bits we use to represent each kind of amplitude, or to store each sample. Then we need to understand what compression is, why it's useful, the advantages. We need to look at different types of lossy and specific types of both lossy and lossless compression, and justify the use of each in a given situation. And then we need to look at compression for text, bitmaps, again, JPEGs, PNGs, vectors. Vectors, the most common format is SVG, and I think a lot of people are probably not familiar with SVG. If you're, if you're not, we're going to look at this. And then also sounds, of course, MP3, WAV, or WAV, etc. Right, so this first class, I mean, we're just going to look at number systems, and in particular, we're going to look at, well, binary and denary. We're going to look at converting between them. Right, we're going to look at, well, when they're used, so, well, binary, denary, hexadecimal. We're going to understand in terms of, well, bits, bytes, and nibbles. We're going to look at a formula for calculating the maximum, let's say the maximum number, right, in any number system, using a given number of bits or a given number of digits. Right, also the range of numbers, again, using that same number of, well, digits, bits. And yeah, okay, right, so, well, currently we're just going to look at unsigned, and when we say unsigned, right, this means only positive. Because, I mean, when we say signed, well, I mean, signed just means what it can have, a plus or a negative, right, it can be positive or negative. Therefore, if we don't have any sign, like if we just say 5, well, we can kind of assume that by default 5 is positive. Because, of course, well, if it's negative, right, we would actually have to write, this negative sign in front of it. Right, we also then need to look at, well, what's the most and least significant bit, and yeah, that's super simple. The most significant bit, well, this is the leftmost bit, right, the one with the highest value. Right, least significant, well, that's the rightmost bit, okay, the bit with the smallest value. And then, yeah, we need to look at, well, how can we calculate the number of bits required to represent a number. So if someone says, well, we want to represent the number, I don't know, 52,743, like, yeah, how would we know how many bits we need, right, in order to represent this? Alright, so yeah, let's have a question then, and of course, I mean, you can pause the video at any point, if you want to sort of try some of these questions, or yeah, try some of these calculations. So let's think, well, do you know what the base of a number system is? And yeah, do you know what base number system we use, kind of in regular day-to-day life? So here, well, the base of a number system is the number of different digits available. So for example, well, okay, like we're going to use base 10, and base 10, well, that gives us what the digits 0 to 9. And well, this is also known as the denary or decimal system. Yeah, I mean, so I guess everyone has really heard of decimals. I mean, denary people have maybe not heard of, but I mean, yeah, I guess, it just means the same thing. And actually in the exam, right, denary is what they're usually going to use. Now, the reason we say it's base 10 is because, well, we see here, right, there's 10 different digits available, right? If we count, well, yeah, 0, 0, 1, 2, 3, right, up until 9, right, that's going to be, yeah, 10 different numbers, effectively. Alright, but then if we look at computers, well, I mean, yeah, like, I guess, do you know what computers use, or, yeah, digital devices? So hopefully people know this, right, computers, well, they're going to use binary, and that's base 2. Right, then, well, let's think, right, so what's stored in binary in a computer? And that actually is kind of a trick question, right? I mean, yeah, the answer is just everything. So that can be, well, numbers, right, it can be text, right, also called strings. And yeah, I mean, I guess, when you're talking about computers, or, yeah, computer science, really you should call text a string, right? So yeah, don't really call it text usually. Right, of course, well, video, audio programs, yeah, I mean, it's all going to be encoded as 1s and 0s. And really a computer actually has no concept of, well, let's say the number 2, right, or the letter A. Because what we'll see is, well, 2 is actually represented in binary, well, it's just going to be 1, 0. Likewise A, so right, capital A, that's going to be 65 in ASCII. So yeah, I mean, we would just represent this as well. I mean, 65, kind of in binary, right? That's going to represent the letter big A. And then, for example, well, small a, right? That's going to equal 97. Right then, if we look at 0, so right, this is the character 0, okay, not the number 0. So I mean, when I say character, I kind of mean like the text 0. Right, so let's say the character 0. Well, that's going to be 48. And I think those, I mean, it is good because actually some questions they do kind of require you to know that. Like, often they won't ask directly, but maybe in a programming question, right, it might kind of be, yeah, I guess it might kind of be assuming that you know what those are, right? So again, well, big A is 65, small a 97, and right, 0 is going to be 48. Anyway, well, back to binary, we say that a 1 value can be considered on or true, right? Well, therefore, a 0 value can be considered off or false. So if we look at how this works in base 10, well, here, we say, well, the first value is going to be 10 to the power of 0. Now, anything to the power of 0 is just going to be 1. Right, then as we go left, we say, well, this power is going to increase. So let's just, okay, right, yeah, let's go the right way. So we see, right, 10 to the power of 1, well, that's going to be 10. Right, now, as we said, since these powers are increasing, well, it's, right, then 10 to the power of 2, right, that's 100. Yeah, 3, right, 1,000, right, 10 to the power of 4, 10,000. Yeah, of course, right, etc. It just goes on, like, infinitely. Right, whereas if we go right, well, probably you can guess, right, it's going to decrease. So then we go, well, 10 to the power of minus 1, right, that's going to be, what, 0.1, yeah, well, minus 2, right, 0.01, right, obviously, etc. So if we think, right, the number 936, well, what does this actually mean in base 10? So what we're saying is, well, it's going to be here, right, yeah, 936. Now, what this is saying is, it's saying, well, I mean, basically we've got, what, 1 times 6, right, or we've got 6 ones, right, then we've got, what, 3 tens, right, then we've got, what, 9 100s, and effectively we're just going to add those together. So, of course, what this is going to be, what, 900, what, plus 30, and then, yeah, plus 6, right, I mean, so, yeah, that's kind of what it means, which, yeah, of course, we can see that there. So, actually, I mean, binary is quite good because, I mean, it's just going to be the same. Now, you see here, again, right, of course, where anything to the power of 0 is just going to be 1. Right, therefore, if we go left, well, then it's going to be, what, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So 2 to the power of 1 is 2, right, 2 to the power of 2 is 4, right, yeah, then 8, right, then 16. So if we notice, right, as we go left, it's just going to double each time, right, yeah, 1, 2, 4, 8, 16, right, yeah, 32, 64, 1, 2, 8, 2, 5, 6, you know, 5, 12. Right, then if we go right, well, then it's just going to half. So of course, what the powers are going to go down by -1. And yeah, the actual values that we represent are just going to half, yeah, or, you know, divide by 2. Now, the good thing to know is that, well, fixed point, right, or floating point, and, well, these are two different ways to represent kind of like non-integer or yeah, kind of real, like, I guess what you say, real numbers or floating point numbers. So actually, right, this is not required for AS, right, that's only going to be for A2. So effectively, like all of this, I mean, you can just ignore this for AS. Since, you know, AS, right, we're only going to be focusing on, well, I guess, yeah, kind of whole numbers, right, when talking about binary. And again, just to recap, so going left is multiplying by 2, right, or doubling, while going right, yeah, like this, right, is obviously, well, dividing by 2 or halving. Right, so let's think, well, yeah, do you know what a bit is in binary? Right, so it's going to stand for binary digit. And of course, well, you can see, right, where they, you know, therefore, right, where they get the term bit. Right, so digits are going to be individual numbers in a Denary system, right, i.e. 9, 3, and 6 in the Denary number, well, yeah, 936. Right, while bits are going to be the individual numbers in a binary number. So, well, e.g., well, yeah, 1001, right, in this binary number, well, this. Right, so... Okay, yeah, right. So, I mean, sometimes they ask up to about 14 digits. Usually they only ask 8. But if we think, well, the first one, what, 2 to the power of 0 is just going to be 1, right, then we just want to keep doubling. The rest of that's going to be, what, 2, 4, 8, yeah, 16, 32, right, 64, yeah, 1, 2, 8, 2, 5, 6, 5, 12, yeah, 1024, 2048, 4096, and what, 8001, yeah, 8192. Now, I mean, people have probably seen these values somewhere. Like, I mean, if you talk about memory, you know, you often see what, like a 512, let's say, gigabyte hard drive. Yeah, or I don't know, maybe you've seen, yeah, I don't know, like 8,192 kilobytes, you know, for some file, for example. I think there's also that game, right? I can't remember, is it, yeah, I think it's the game just called like 2048, where you're using some squares, like on a grid. And I mean, actually, for me, I've never played it. But yeah, I think you have to sort of combine them somehow, right? Do some calculations, and again, you know, of course, like because, well, somehow that game must be using the powers of 2, right? Therefore, that's why you're getting these values. Yeah. So again, well, sometimes exams will go up to about, let's say, sort of, well, 14, you know, 14 times, because, well, obviously, well, 0 to 13. So yeah, as in, like, you know, a power 0 right up until power 13, right? That's 14 times. However, usually, I guess we're only going to have probably 8 different numbers. So in this case, well, yeah, I guess let's say, well, go up to 7, right, in terms of the power of 7. But yeah, of course, right, you know, 8 different bits. And then, well, let's think, right, so why do they use 8 bits? I mean, yeah, what is, like, 8 bits? Right, or, yeah, what's another name for 8 bits? So, yeah, maybe people know, right, but 8 bits is just also called 1 byte. And let's say, for example, if you see, let's say, a lowercase b, well, a lowercase b, right, this means bits. Whereas, let's say, if we see, let's say, an uppercase b, well, an uppercase b, right, that's going to mean bytes. So if someone says, well, what's bigger, like, you know, 10 MB, right, or, well, yeah, I guess, you know, 2 megabytes. Well, actually, like, of course, a lot of people are going to think, you know, this one is bigger. Like, I don't know, if you see some, like, yeah, internet download speed or some, you know, phone contract that's offering, I don't know, yeah, like 100 megabits per second. But in reality, you know, this one is, of course, going to be bigger because, well, if we multiply this by, right, if we multiply this by 8, well, of course, right, this is going to be equal to well, let's say 16. Now, in this case, right, this would be megabits. we'll also look at something else where it's going to be called, well, maybe bits. And yeah, that's going to be another unit which we'll look at probably, yeah, I don't know, maybe in a couple of classes. So again, well, just to recap, then a bit is going to be one binary digit, I would say, well, just a 1 or a 0. Right, a nibble, well, this is going to be 4 bits, right, e.g., well, yeah, like 0, 1, 1, 0. And then a byte, well, that's going to be 8 bits. And I think, you know, bit and byte people can usually remember, you know, nibble sometimes people get confused about. But if you think, well, like, what is a nibble, right, just, you know, it's kind of regular English. I mean, if you're talking about, like, eating food, well, you say, well, I know what the crocodile had, like, a big bite of the, I don't know, yeah, the person, right, yeah, but like a big bite of their leg. But you'd probably say, what, like, a mouse had a small nibble, you know, on some cheese. So, yeah, that's kind of what we say, right, a nibble is just going to be a small bite. And, of course, well, bite with an I here, right, since we're talking about, you know, eating food. Yeah, e.g., you say, right, a mouse nibbles on cheese. So the way you can remember it is, well, a nibble is just a small bite. Or, yeah, in particular, what it's going to be half a byte. And I suppose here we should say, well, a byte is going to be 8 bits again. Yeah, or 2 nibbles. Right, so let's look if we want to calculate Denary numbers. So if we have, what, 8,492, we say what is each digit, right, it can be thought of as being each digit multiplied by the Denary positional value. So in this case, again, what 8 times, what, 10 to the power of 3, right, that's going to be 1,000. So of course, well, yeah, 8 multiplied by 1,000, right, 8,000. Obviously 10 to the power of 2, right, that's 100, right, 10 to the power of 1, well, that's just 10. And 10 to the power of 0, right, that's 1. So of course, yeah, well, we're going to do all of those multiplications, right, add them all together. Yeah, that's going to get our number. Now, I mean, the convenient thing is that actually for any number system, so whether it's binary, hexadecimal, you know, well, base 64, some random, you know, base 17, right, just, yeah, completely, like, arbitrary, right, I mean, it's all going to be the same approach. So what we're saying then, well, in binary, we say, well, again, 2 to the power of 0 is going to be 1, 2 to the power of 1 is going to be 2, right, 2 to the power of 2, yeah, 4, right, 2 to the power of 3, 8. So, okay, I mean, right, let's say this is our number, right, 1001, and we want to calculate, well, you know, what does this binary number equal in Denary? So what we want to think is that, well, here what we're saying is what we've got kind of 1 times 1, right, then, well, 2 times 0, right, is 4 times 0, and then, yeah, 8 times 1, or 1 times 8. All right, then, of course, we just want to add all those together. So if we have that, well, of course, I mean, here then, right, that's just going to equal to 9. And if you think, well, we can actually simplify this because, well, of course, anything multiplied by 0 is just going to be 0, right, therefore we can eliminate this, right, likewise, we can eliminate this. Likewise, well, anything times by 1 is just going to be the same. So, yeah, I guess, well, in effect, we can just eliminate this 1. Yeah, well, we can also eliminate this 1. And then, of course, well, that's going to give us, well, just 8. And then, well, let's say plus, and then, yeah, this 1. So, yeah, I mean, in some ways, binary is actually even easier because, well, we don't really have to worry about the multiplication. Yeah, we can just add them. Yeah, I mean, so hopefully that makes sense, right? Or, of course, anything multiplied by 0 is 0. Anything multiplied by 1 is just going to be itself. So, basically, you can just remove that and, yeah, just add them. Right, okay, so, yeah, okay, well, we said binary is base 2, Denary is base 10, and again, this just means the number of different digits, right? So binary is base 2 because, well, we only have, what, 2 digits, 0 and 1. Base 10, well, of course, well, 0 up until 9 are 10 different digits. So can you guess what the bases, well, octal and then hexadecimal are going to be? So I think hexadecimal we've said. Now, I mean, hex, you can think, well, hex is going to mean 6. If we say, well, I mean, sort of, well, yeah, I guess like dec, or yeah, like deci, right, that's going to be 10. Now, I mean, like, this is not going to be 60, right? It's actually going to be 16. But yeah, again, you can kind of see, right, well, we've got the 6, right, we've got the 10, right, so yeah, 16. And then, well, oct, I mean, if you think, well, oct, right, that, of course, just means 8. And we see, actually, yeah, octal, right, that's going to be rarely used. However, hexadecimal, well, yeah, this is going to be extremely common. And we can use this, well, to represent colours, right, also, well, IP version 6 addresses. Right, there's going to be something called, well, IP version 4, which is going to use Denary. But yeah, IP version 6, right, this is kind of like improved, right, there's going to be more, well, yeah, more addresses available. Right, this is going to be represented in a human readable form using hexadecimal. Right, something called MAC addresses, and again, right, I mean, well, these things, you know, we're going to cover in Unit 2, right, networking. But MAC addresses, well, this will just be, I guess you say, what, a unique identifier to uniquely identify that device, or yeah, to uniquely identify, let's say, the network card or the, yeah, wireless network interface card. And yeah, well, okay, so I mean, this is going to be what 12 hexadecimal digits, right? Well, the first six are going to be assigned by the manufacturer, right? Then the last six, well, they're going to be unique for the device. So yeah, it's going to be kind of broken into two parts. Right, also memory addresses, yeah, we can represent. And I don't know, like maybe, well, I guess if people have used any sort of like debugger, right, disassembler, they would have seen that. Maybe something that's kind of more, I don't know, like more common, well, unless you're like hardcore into programming or something, and yeah, like unless you've actually used those things already. But maybe something people have used is something like cheat engine. And I mean, this can be used, right? Let's say you're playing a game, and I don't know, you have some sort of like money in the game. I mean, not real money, but just of course, yeah, the kind of virtual money, right, in the game. Now, let's say you just want to increase that money. Well, you can use cheat engine, right, to inspect the memory addresses. And let's say, for example, I don't know, so your in-game your in-game currency is like, I don't know, 17,854. Well, what you would do is you would just search for this address, right, in all of the memory locations that are being used by that game. Right, then of course you can just modify this value. So I don't know, let's just say you want to add like an extra couple of zeros, yeah, just to increase your money in the game. And I mean, if you do this, well, cheat engine, you'll notice, okay, this is going to use hexadecimal, right, to represent the memory addresses. Also, other things called hex editors. So what you can use, well, you can use a hex editor to inspect inspect the contents of any file. And the thing is, well, of course, it's going to be binary contents. But since representing in, like 0, 1, 1, 0, 0, 0, right, it's going to be so complex for humans. So just to make it more readable for humans, right, that's why it's written in hexadecimal. And the thing to note is that, well, even we say, right, it's represented in hexadecimal, this means, I mean, just represented for humans, right? Like, I mean, kind of, again, like, still within, kind of inside the computer, right, it's still going to be using binary. But yeah, we're just talking, well, when it's, written down on paper, or yeah, when it's like displayed on screen. Right, it can be displayed in hexadecimal, right, to make it easier for humans. All right, so hang on, let's how do I clear this? I think this one. All right, then, well, base 64. So actually, I mean, this is actually not in the exam, although yeah, this is also useful kind of in real life, right? It's commonly used. So well, one thing it's used for is converting, well, let's say raw binary, right, to ASCII, and vice versa. Now, if people have actually used the Pseudocode website, of course, that I guess I made. So, right, if people use that one, then when you share a file, then you might notice that you get, I don't know, I think the URL is like code, and then equals, right, and then it's going to be some huge random string of text. Now, basically, this code, I mean, what this is doing, it's just taking the code that you actually wrote, right, the pseudocode that you wrote, right, then just converting it into base 64. So I mean, I guess that's one case where base 64 is actually used, right, if people have actually shared any of the code, using the share button right on the website. Right, okay, well, of course, you can also create your own base, right, if you have a purpose, e.g. generating random IDs, right, encoding, encryption. So yeah, maybe if you want to go, well, we want to use base 7, right, for this particular purpose, then of course, you can easily do that. Right, and also, well, spreadsheet programs like, let's say, WPS, Microsoft Excel, I think OpenOffice, right, they actually use base 26. And yeah, I mean, have a think, right, see if you can figure out where they're using this. Right, so if we look, well, it's going to be the columns. So the columns you see, well, it's going to go A, B, C, right, then when it gets to Z, it's not going to go, for example, I don't know, like, I don't know, 1A or something like that, right, it's just going to go to AA, AB, AC, right, etc. And of course, when it gets to AZ, well, it gets to AZ, right, then it's going to go to B. So guess what, then it's going to go, BA, right, BB, right, of course, etc. Right, so in other bases, like we said, we're required to multiply, right, I think this we've looked at already. Right, this is kind of more complex with hexadecimal base 16, or base 64, or some other arbitrary base like base 9, because, well, again, you've got to do, I don't know, right, let's say you have the position, right, 64 to the power of 4, and I don't know, let's imagine you want, let's imagine you want, for example, t of those, right, well, that's going to be quite complex, because, you've got to think, well, one, right, what is t, and also, of course, what is 64 to the power of 4, so, of course, I mean, obviously, right, the bigger the base rate is going to get more complex, although, of course, for computers, right, it doesn't really matter, since, computers are pretty good at calculations. Right, so yeah, I mean in binary, well again, since we said, right, we're multiplying by 0, which is just, well, yes, obviously doesn't do anything, multiplying by 1, where it just stays the same, then we can kind of shorten this in binary, where we just have to add the values together. Right, so let's look at this then. So let's say here, this is our binary value. Well, we just want to add this, so we've got what, 1 8 1 4, right? We've got no 2's and then 1 1. So I mean, I'm just adding this. Then of course what we can see, well, 8 plus 4 is going to be 12, right? Plus 1, that's going to be 13. Right, and then I would say just pause the video, okay, try and do these next two by yourself. So, all right, I mean, if you've done that, then where you see the next one, well, 4 plus 2 is just going to be 6. And then what are the last one? Well, 8 plus 4 plus 2 plus 1, right, that's going to be 15. And some of these, you should start to remember, like if we have 4 bits and they're all 1s, right, then it's going to be 15. If we have 8 bits and they're all 1s, right, it's going to be 255. Yeah, so some of these common ones, I mean, you should start to remember. Right now, again, it's just the same process. So what, just 128 plus 64, so that's going to be what, 192. Right, no 32s, right, then plus 16. So that's going to be what, 192, right, then 208. Right, plus 8, 216, plus 4, right, 220, right, plus 1, right, should be 221. And again, right, this one you can do by yourself. Alright, so if you've had a go at that, well, this one we can see, right, actually it's all just 1s. And when we have all 1s, well, yeah, and if we have 8 bits of all 1s, right, that's going to be 255. And of course, yeah, you can add this just to verify. Yeah, and I will actually just give a hint here. So one thing you can see is that, right, okay, let's say here, right, if we just look at these first 4 bits. Now, if we add all of these, right, these are going to equal 1 less, right, than the next position. So we see the next position is 16, right, therefore if we add all of the bits to the right of that, right, it's going to be 15, right, it's going to be 1 less than 16. Likewise, for example, let's say we look at 64. Well, if we add, right, all of these bits here to the right of 64, well, again, using the same rule, okay, it's going to be 63. Likewise, if we think, well, right, well, of course, if we go 2 to the power of 8, right, 2 to the power of 8 is therefore going to be 256. Right, that's why if we add all of the bits, right, to the right of 256, well, that's why it gives us 255. Because, of course, yeah, 255 is 1 less than 256. So, yeah, and that's going to be something that's going to be useful to know. Right, okay, then let's look at the maximum number that we can create with n bits in binary. And, of course, well, again, right, a bit is just a binary digit. So well, how many bits are in a nibble and how many bits are in a byte, right? Hopefully people can remember what a nibble is, a small byte, right? Therefore 4 bits, or yeah, half a byte. Right, a byte is going to be 8 bits. Right, then the question, what is the maximum number we can store in a nibble and byte respectively? So, of course, like, well, I mean, maybe you're going to look at this and you think, well, right, I've just got no idea. But, of course, I mean, just think about it logically, right? If we got a nibble, well, the biggest number we can represent is just going to be, what, 4 1s, right? Just adding everything together. As we said, this is going to be 15 in Denary. Likewise, a byte, we said, well, that's going to be 8 1s, and 8 1s is going to be, well, 255. Now, what we want to think then, well, is, yeah, okay, so, okay, right, this one, right, is there a formula we can use to calculate the maximum Denary number that we can represent with 8 bits, or, well, okay, sorry, with n bits? So let's say if someone said, well, right, okay, we have 10 bits, right, what's the maximum Denary number we can represent? Alright, so yeah, I probably shouldn't have clicked next. Now, I guess a good way of solving this is, well, just try different values. So let's say if we have 1 bit, well, 1 bit, well, I guess the biggest number we can represent is just 1. Right, so let's write that here. If we have 2 bits, well, we can have 1 1. Alright, so that's going to be 3. Hang on, right, okay, right. If we have 3 bits, well, 3 bits is going to be 7. Right, 4 plus 2 plus 1. Alright, 7. Right, if we have 4 bits, well, it's going to be 15. Right, if we have, what, 5 bits. It's going to be, right, 31. Yeah, if we have 6 bits, it's going to be, what, 63. So what you want to do, well, I mean, yeah, obviously you want to look at this pattern, and, well, from this pattern, can you see a formula? And I suppose what you can think is, I mean, what basically it's kind of doubling, although actually it's kind of 1 less than doubling, right? Because, like, okay, well, yeah, I guess, like, let's imagine, like, if this was 2, for example. Well, then if we double it, right, it's going to go to 4. But yeah, this is 3. Right, likewise, yeah, if this was 4, well, then we double it, it goes to 8. Right, but then, again, right, this 7 is 1 less than 8. Yeah, that's probably a terrible explanation. But I mean, from this, you should be able to see, right, it's going to abide by this, right, 2 to the power n minus 1. And when we say the n, well, this is our n here, right? So let's say if we say n is 5, well, 2 to the power of 5 is going to be 32, right? Therefore 32 minus 1, right, that's going to say 31. So 31 is the biggest number we can represent using 5 bits. Right, therefore you think, well, yeah, going back to our original question, right, what's the maximum we can do with 10 bits? And I think 2 to the power of 10 is going to be 1024. Right, therefore, of course, well, the biggest is going to be, what, 1023? All right, and, well, okay, yeah, let's try this then. So what is the maximum number we can store in 2 bytes? So 2 bytes, well, remember, a byte is going to be 8 bits, right? Therefore, 2 bytes is going to be 16 bits. So it's then, well, 2 to the power of 16 minus 1. And I mean, honestly, like this, you'd probably have to do on your calculator, to be honest. I mean, I guess you could do it just by, doubling. But yeah, if you do that, right, it's going to equal this. And to be honest, this is something you might remember. Now, again, if we say, what, 1 byte, the biggest is going to be 255. Right, with 2 bytes, the biggest is, 65,000, right, 535. Right, then if we say 3 bytes, so 3 bytes, what, or 24 bits. I mean, I can't remember exactly, but it's something like maybe 16.6 million, or yeah, I think maybe 16.7 million, right, something like that. Right, then if we say 4 bytes, so 4 bytes being 32 bits, 4 bytes, I think it's maybe 4.2, or yeah, maybe 4.3 billion. And we see this is actually useful when talking about IP version 4 addresses, because IP version 4 uses, well, 32 bits. Therefore, that means, well, we only have, right, 4.3 billion different IP addresses. But the problem is, well, there's going to be, what, 8 billion different people, or I don't know, maybe like 8.2 billion different people. And honestly, like, many people have multiple devices, right? People have, let's say, well, they have a phone, they have a laptop, yeah, maybe they have a desktop. Even now, for example, cars, right, many cars are going to have an IP address. Even things like, yeah, some sort of, smart fridge, right, some home appliance. So of course, yeah, let's say 4.2 or 4.3 billion IP addresses. Right, that's not going to be enough. Right, so, well, do you think then a similar equation to 2 to the power of n would work for Denary? So, right, if you've had a thought about that, well, yeah, that's going to be yes. And here we just say, well, 10 to the power of n, right, minus 1. And this is actually kind of more intuitive, to be honest, because, well, with 1 digit, right, the maximum we can represent is 9. And of course, well, 10 to the power of 1 is going to be 10, right? Therefore, well, 10 minus 1 is 9. Right, of course, well, with 2 digits, right, the maximum 99, yeah, 3 digits, right, yeah, 999. So I think, I mean, yeah, hopefully you can see how this makes sense. So if we think about the general formula, well, right, hopefully you can see what it's going to be, well, b, right, where b is the base, right, to the power of n minus 1. Yeah, all right, so let's just skip that. Right then, for example, right, if an exam has to calculate the highest number that could be represented with 20 hexadecimal digits, right, what would the answer be? Now, actually, the exam would never ask this because, well, 1 is going to be a huge number, right, and, well, 2, the exam doesn't have a calculator, right, so it's a non-calculator exam. But if you think about the formula, well, the formula, right, b to the power of n, right, therefore, well, what the base is going to be 16, and, well, the number of digits is 20, yeah, therefore, right, of course, it is going to be this. Right, then if we look at the range, so if we have 4 bits, right, the maximum we can represent was going to be 15. Right, so with 4 bits or a nibble, right, what's the range? So the smallest and then biggest we can represent. So again, I mean, logically think, right, well, the smallest is just going to be, what, 4 zeros. So you say, well, the range is going to be 0 to 15. Right, therefore, how many different numbers can we represent? So if we think, well, here, right, the number of different numbers is actually going to be 16. Because if you think, well, all right, yeah, 0, 1, 2, 3, 4, 5, 6, 7, all right, up until 15, right, that's going to be 16 different numbers. So, right, this time, can you think of a generalized or, well, binary specific formula to calculate all of these features? So, yeah, let's go next, right, and again, pause it if you want to try and calculate this. Right, so the number of unique values, well, this is just going to be 2 to the power of n. Like we said, right, when there's 4 bits, well, 4 bits can give us 16 different values. Right, and of course, what 2 to the power of 4 is going to be 16. Likewise, if we have 1 byte, well, 2 to the power of 8, that's going to be 256. So yeah, this is the maximum number that we can represent using 1 byte. And if, for example, people are familiar with colors, like let's say like HTML color codes, then you might have noticed that we can represent, well, from 0 to 255. Right, that's going to be the different yeah, the different component values, right, for red, green, and blue. Yeah, and also, well, the alpha, right, or the opacity. And well, yeah, I mean, when I say the opacity, right, that just means the transparency, so whether you can see through or not. Right, then the maximum, well, the maximum we said, what, 2 to the power of n minus 1. Right, and then the range, well, what the smallest is going to be 0, and then what the biggest, well, of course, is just this maximum. And I mean, hopefully you can see, well, of course, well, this is 2 to the power of n, right, this is 2 to the power of n, you know, then just minus 1. So, I mean, like, yeah, of course, I mean, these are pretty similar, really. Yeah, likewise, the range, well, of course, what, just 0 to the maximum. So yeah, hopefully this is not too difficult. And again, right, these formulas work for any base, right? If you want to do this in the exam for base 16 or base 10, right, then of course you can likewise do that. Right, so yeah, let's just erase that. So why do the maximum range formulas contain the minus 1? And the reason for that, well, as mentioned, right, that's because, well, there's also, well, I guess, yeah, one of the numbers is 0. So let's say if we just had 2 bits, well, 2 bits, right, we can represent these different values. So what, 0, 0, right, also 0, 1. And well, let's just write these. So, well, 0, 0 is going to be 0, right, in Denary. Yeah, 0, 1 is going to be, well, 1 in Denary. Right, okay, 1, 0, right, that's going to be 2 in Denary. And then, well, 1, 1, right, that's going to be 3 in Denary. So again, we see, well, of course, right, the smallest is 0. The biggest is, what, 2 to the power of n minus 1. And then, yeah, the number of different values, well, that's 4. And of course, well, 4 is, what, 2 to the power of 2. Yeah, since we're using, what, 2 different bits. Okay, so, well, okay, yeah, right, we've seen how to go from binary to Denary. Now let's see how to do the reverse. All right, so Denary to binary. Right, so if you want to convert the number 9 into binary, then I guess kind of informally, well, all you do is just add the values up, right, starting from the left, right, until we reach our target number. If you want to write this more formally, you say, well, we start from the left. If our target number is greater than or equal to the Denary positional value, then we set the bit to 1, right, while if it's smaller, we set the bit to 0. Right, if we set the bit to 1, we then subtract the Denary positional value from the target number. So honestly, like, this is quite wordy, and basically, I mean, it's just saying the same as this. Now, if we see an example, of course, right, this is going to be quite easy. So again, right, if of course we want to represent 9, so what we're doing is again, right, starting from left to right. So we're going to say, well, is 9 bigger than 8? Now in this case, what, 9 is bigger than 8, right? Therefore, of course, well, that means we need a 1 here. But right, since we've had an 8 here, well, then what we want to do, we want to do 9 minus 1. Okay, sorry, okay, right, yeah, 9 minus 8. Right, yeah, since we've used an 8 here, right, that's going to give us 1 remaining. Right, so well, then we go right. And we say, well, yeah, okay, like, yeah, okay, right, let's say, is this 1 bigger than 4? And of course, well, that's going to be false. Or, yeah, greater than equal. Right, likewise again, right, so, yeah, is the 1 greater than or equal to 2? All right, that's false, right, so we add a 0. And then, of course, we get to the last one, well, is 1 greater than or equal to 1? All right, that's true. Right, therefore, of course, we add that 1. Now, yeah, I know, like, maybe when I say it like that, maybe it's quite confusing, but I think if you just use this, right, add up the values until you reach our target number, yeah, then it should be quite simple, hopefully. And again, this is just kind of what I've explained here. Right, so let's have some practice, right? Let's say if we want to represent 7. Now, right, I mean, let's think of our positional values. We've got 8, right, then we've got 4, then we've got a 2, then we've got a 1. Now, some people, they start counting from right to left. But yeah, this is actually not going to be good because, well, sometimes you'll get the wrong answer because I don't know, maybe you've sort of like added 2, or yeah, I guess you've like missed out one of the numbers or something. So yeah, okay, that's why you want to go right left to right. So we think, well, of course, right, to make 7, well, of course there can't be an 8, right? An 8 is too big. Right then, okay, then there will be a 4 because well, 7 is bigger than 4. All right, therefore we're going to have, what, 3 remaining, and well, 3 is bigger than 2, right? So of course there is going to be a 2. Right, then we have 1 remaining because, of course, well, we minus the 2. Right, therefore, of course, well, there is going to be this 1. Right, now, let's say, I mean, well, I think actually, yeah, 9 we've just done. So, again, yeah, try and do this one yourself. Right, then, yeah, if you do that, well, it should just be 8 plus 1. Right, then let's try 13. Again, try this yourself. Pause the video if you have to. So if we think, well, 13, right, that's going to be, what, 8 plus 4, that's 12. Right, then plus 1, that's going to be 13. Right, okay, then, okay, yeah, let's say in later units, particularly logic circuits, you'll need to list all the different input combinations. The simplest way to do this is to simply count in binary. Right, and the task, well, write all the combinations of 4 bits by counting in binary. And what number will you need to count to? So this is saying, well, if we have 4 bits, right, what's going to be the smallest number? So the smallest number is what going to be, well, 0, 0, 0, 0, which of course, well, it's just 0 in Denary. Right, the biggest number, well, it's just going to be, you know, all ones. Right now, all ones, that's going to be 15 in Denary. So what we want to do, well, we want to write out every binary combination. So effectively, you know, 0, 1, 2, 3, 4, yeah, right, etc. Right, up until 15. And yeah, just write out the binary code for that. So again, right, just pause the video, and then of course, yeah, when you've done that, right, then just resume, right, and check the answers. Okay, so let's just have a look then. Right, so if you've done this, I mean, this should be what you get. And again, I mean, well, one, it's just good practice because, like, honestly, right, in the exam, they always ask, you know, questions, right, binary to Denary, yeah, Denary to binary, yeah, sort of binary to hex, you know, just converting all of them. And also, again, when it comes to logic circuits, okay, you will, yeah, you will often need to write these out. Although, yeah, sometimes they do actually give them to you, to be honest. Right, so I guess, well, I mean, yeah, first, like, I mean, yeah, like, honestly, I mean, of course, right, everyone's going to be slow at first. But with practice, I mean, you will get quicker. And, I mean, once you practice, I mean, you will actually notice some patterns. So, for example, one pattern is, well, if you set a left bit to a 1, then all the bits on the right will become 0. So, for example, when we go from 7 to 8, right, well, what we're going to do, right, we're going to be setting this bit here to, well, to a 1, right, to represent the 8. Right, therefore, all of these bits on the right, okay, all of them are going to become 0. Again, you know, likewise, there's going to be other sort of patterns that you notice, right, just with more practice. All right, so let's do the same, but just some more difficult questions. Right, if we want to represent 37, right, again, pause it, have a go. Right, so let's think then, well, of course, yeah, I guess what 128 is going to be too big, 64 is too big. Then here, well, so to make 37, right, of course, there will be a 32. Right, there won't be a 16 because, well, if you think, right, we only need to make 5 now. Right, of course, well, 8 is too big, right, but then 4, so there will be a 4. Right, this gives us 1 remaining. Right, there won't be a 2, but then there will be a 1. And again, you know, these questions are quite easy to check because, of course, well, once you've done this, right, just add them up again. So here, well, 32, right, plus 4, well, that's going to be 36, right, plus 1, right, yeah, that's 37. Right, and then I think this one, right, try yourself, right, 148. Right, again, so if you've done that, well, of course, this one, it's going to be 128, right, then we want a 16 because, well, 128, right, then we're going to have 20 remaining. So to make the 20 remaining, it's going to be a 16 and a 4. And yeah, of course, right, all the others are going to be zeros. All right, and then wait, do we not have the, okay, there we go. Right, so yeah, 239. And again, just try this. Right, so this one's going to be more difficult. I guess if you just do that, add them all up, right, that should be 239. And there's actually a quicker way we can do this. Because if we think, well, the maximum value we can represent with 8 bits is going to be 255. Therefore, we can kind of check our answer because we can think, well, 239 is what's 16 less than 255. Yeah, or in effect, what if we do right, 255, right, minus 239. Well, that's going to equal 16. Therefore, what we can say is, well, all of the bits have to be set, right, except for this one here. Yeah, you know, since again it's 16 less. Now, if it was 20 less, what you so for example, if it's 235, then to be 20 less, of course, what we say, right, this 4 would also be a 0. So again, you know, just kind of spotting these patterns, right, is going to make it easier to check your answers as well. Right, then if we look at this, and this one's super simple, right, so the most and least significant bit, yeah, these terms are sometimes mentioned. Right, the most significant bit is the bit with the highest value, i.e. the leftmost, while the least significant bit is the bit with the lowest value, right, i.e. the rightmost. So in this case, well, here, if we're using 8 bits, right, 1 byte, the most significant bit is going to be, well, let's say bit position 8, right, that's going to be what the value of 2 to the power of 7, right, or yeah, you know, 128. Of course, what the least significant bit, well, that's going to be this one here, right, bit position 1, of course, right, just with this value here of 1. Yeah, of course, I mean, here bit 8 is the most significant bit. Yeah, bit 1 is the least significant bit. Now, let's say, for example, of course, like, I don't know, right, let's say we're only doing a nibble. Then, of course, right, in this case, well, here, right, for this nibble, well, bit 4 would be the most significant bit. Likewise, of course, if we were using fixed point. Now, again, fixed point, this is going to be to represent, well, floating point or real numbers. Right? I mean, basically, yeah, decimal numbers. Yeah, I guess kind of, right, non-integers. Now, that's only required for A2. But let's just say, for example, in that case, I don't know, maybe we have 1 1, right, 0 0, right, and then let's say the point, and I don't know, let's say, I don't know, like 0 1. Now remember, right, of course, this is going to be 0.5, this is going to be 0.25. So in this case, what, right, this again is going to be the least significant bit. So what, yeah, representing 0.25. And what the most significant bit here, well, that's just going to be representing 8. And right, this is again only in unsigned. Right, if we're using negative, then we'll see it's actually slightly different. But yeah, currently, right, just for positive unsigned, right, it's going to be 8. And yeah, note that we usually count from right to left. So again, just saying, well, right, this here is bit position 1, right? Then we're kind of getting bigger going from right to left. So I mean, don't do this, right? Don't go, this is, you know, bit 1, bit 2, bit 3, bit 4, right? It's actually the other way. So kind of, yeah, the smallest value is going to be bit 1, right? Then the biggest value is going to be, well, in this case, bit 8. Right then, well, we can also look at removing the leading 0. So take the Denary number 3 in binary. Okay, so with 1 byte, then it's going to be this. So what, just 2 plus 1. Then of course, what, yeah, no 128s, no 64s, right? No 32, 16, 8, and 4s. So I mean, basically, we've got kind of a lot of wasted space. So for unsigned positive binary values, then we can actually simplify this just by writing it as 1 1, because of course, well, yeah, I mean, these leading zeros, right? They just don't do anything. However, right, if we're using signed, and again, right, signed, this is going to mean, well, negative or positive, which, well, currently we've not looked at. But, yeah, I mean, if you're sort of viewing this video as a recap, then, well, when we're using signed, right, we would also need the leading 0, right, just to keep it positive. Because, well, otherwise using signed, right, the first bit is going to be negative, right, using signed. So using signed, it would become, well, minus 2 and then 1, right? And of course, if we add those, well, it's going to be minus 1. So yeah, of course, right, therefore with signed, right, we do still need that leading 0. Right, so let's see, if we want to represent the Denary number 129, then how many bits would we need, right? And let's see how to calculate this. Right, okay, so yeah, let's just see that. Right, so the formula wise, it's going to be the number of bits required is going to be, well, this thing right is called the ceiling function, right, of log 2 base n. Now, right, yeah, this kind of ceiling function, right, well, this just means round up. So for example, if we have, well, right, the ceiling of, well, 3.0001, right, that's just going to round up to 4. And I mean, if you think about that, like, that kind of makes sense because, well, let's say, for example, I don't know, maybe we want to represent the number 9. Now, I think, what, log base 2 of 9, that's going to be like, right, 3 point, I don't know, yeah, 3 point something. Because if we say, what, 2 to the power of 3 is going to be 8, right, therefore, since 9 is bigger, well, it's going to be, yeah, 3 point something. But, of course, if we only have 3 bits, well, that's not going to be enough because, what, with 3 bits, we go, what, 4, 2, and 1, right, therefore, with 3 bits, you know, we can only represent 7, right, that's why we need to round up and use 4 bits. And then if we use 4 bits, well, again, we can represent up to 15, and, of course, well, 15 is going to be bigger than 9, right, therefore, that's okay. Right, so let's try and do that then. Right, how many bits would we need to represent the Denary number 129? Right, so, I mean, of course, right, if you're using that formula, then I guess, is that going to be 7 point something? Because, what, 2 to the power of 7 is going to be 128. So, yeah, it's going to be just above that. Yeah, so I guess, right, it's going to be this. And, of course, well, right, ceiling, rounding up, we're going to round that up to 8. Yeah, and to be honest, like, another way you can do it, which I think we'll see in a minute, actually. Yeah, so, well, I mean, remembering the formula is good since you can easily calculate the number of bits to represent huge numbers. For example, the number of atoms in a universe. So, yeah, I would actually say, I mean, try this, right? I think the number of atoms in the universe is approximately, yeah, right, let's say it's approximately, like, you know, 10 to the power of 80, right? I mean, that's what I've seen as estimates. So, yeah, I mean, you know, try and actually calculate this. So again, what you want to do, what, log base 2, and I guess what, of this number, and yeah, of course, right, find out how many that is, right, okay, then ceiling, so yeah, then just round it up, right, I mean, see how many bits you would need to represent that, and I think it's going to be about, like, 300 and something, because, yeah, you sort of multiply by 4 usually. Right, yeah, so I guess, well, for small numbers, and let's just erase this, hang on. Right, for small numbers then, well, you can kind of intuitively think of it. Right, if the target number is greater than the current binary positional value, but less than the next, right, then we need this number of bits. So that's quite wordy, but again, right, if we see an example, and again, right, this is just repeated. Right, is there an example? Okay, right, so how many bits are required to represent the number 56? Now, let's think, well, of course, I mean, obviously, right, 1 is not big enough, 2 is not big enough, 4 is not big enough, right, 8 is 16, right, 32. So, right, okay, well, yeah, if we think, I mean, 32 is obviously not bigger than 56. But then, right, now if we go to 64, then, well, 64 is bigger than 56. So actually, 64 is actually going to be too big. So, I mean, I guess probably a better way to say it is, well, you're just going to go in the middle. So, I mean, since 56 is, less than 64, right, but bigger than 32, yeah, it's going to be in the middle, right, therefore, well, yeah, this is how many bits we need. And remember, the reason for that is because, well, as we said that, okay, right, let's take a position, and then all of the bits to the right of that are going to add up to, what, 1 less than that value. So if we say here, right, I mean, since this is 64, then if we add up all of the values to the right of it, well, that's just going to equal 63. And again, of course, you can do this, right, 32 plus 16 is, right, 48. Right, then plus 8, right, that's going to be, 56. Yeah, plus 4, right, 60, right, 62, 63. Yeah, so I mean, I guess, like, hopefully you can see that if we need 56, well, I mean, we don't need to go to 64, right, since that's going to be too big. And of course, well, if we go to this, right, 32, so again, right, using 5, okay, right, sorry, yeah, using 6 bits, right, then, yeah, 6 bits is going to be big enough. Yeah, and then, right, so, well, let's try this as well then. So let's try 127. Now, using this logic, well, 127, what we're only going to need to go to 7 bits. Because if we add, well, 64, 32, 16, 8, 4, 2, and 1, right, that's going to be 127. But then if we want 128, well, 128, we're just going to want this. And actually 128 wise, it's just going to be, what, 1, and then, well, yeah, 0, 0, 0, 0, right, yeah, yeah, of course, right, those are all going to be zeros. Alright, so yeah, I think actually that video has been longer than I expected. Now, obviously here you can see, well, in the next video we're going to cover hexadecimal. For this video, well, we're just going to finish there. Now, as always, right, if you have any questions about that, well, just ask in the comments. And yeah, if the video is useful, then, well, hopefully see you in the next one.